Hi, this is Erik Peterson, and this is my paper report on the SSH paper, Timing Analysis of Keystrokes and Timing Attacks on SSH. It's a paper about an attack on the SSH protocol. SSH is I'll get to it in a second, but it's a method of remotely logging in to another machine uh, on Unix-style platforms. This attack uses machine learning to guess at a user's password. And in the rather limited trials they show that you could get a roughly 50 times reduction in the number of passwords you have to check. I'm not completely sure that's going to scale. I'll get to that in a little while, but that's something to certainly a big improvement if you can, instead of on average dealing with 50% of the passwords, having to brute force check 50% of the passwords. If you get that down to 1%, that's obviously a big deal. So a little bit more about SSH. It was created in 1995 as an encrypted way to remote log in to other machines, especially Unix and then later Linux and machines like that. What makes the attack possible is that after you do your initial login, every character you type gets sent to the server individually. So, and this is probably done, this is 1995, so you still have mostly dial-up connections. And so to encourage responsiveness and improve performance, getting those characters out as fast as you can, as soon as you can, certainly helps. And then, but in addition to that, responses that come back aren't padded very far. So you can get both the timing of the individual keystrokes, even though they're encrypted. You can see each keystroke coming across the line, and you can also get a general idea of the size of the responses. So it lets you figure out, from what the paper says, pretty easily figure out when the user is doing a command that's going to require a second password. And that password is sent, just like everything else, one character at a time. So if you can figure out when a second password is put in, then you know what to capture and what to analyze to try to break that password. As I said in the last slide, the key to this attack is the timing that you can get, or the individual keystrokes you can get, and more particularly the timing you can figure out, because they're sent as soon as possible. So you can tell how long it takes between one character and the next. And in fact, the paper made sure that the typical network latency is quite a bit less than the standard deviation of these character latencies, these between character latencies. And from that, and as we'll see as we go along, from that you're able to make a pretty good guess as to at least which types of characters you're doing, so you can really narrow down the possibilities of what the user is typing based on how long it takes them to go from one letter to the next. Because this is a machine learning algorithm, we have to train the algorithm in order to figure out what the keystrokes are. So what the paper did, the authors did, is they had users repeatedly type two different characters, and they did this they used a total of 15 characters. And so they did the difference between each pairs and had a user type it many, many times to get an idea of how long it takes them to go from one character to the next. Now these between character latencies showed a Gaussian distribution, and as I said earlier, the standard deviation of these latencies is a lot more than typical network latency, so the fact that one packet might be a little later than another one is not a big deal. And they also found that certain key combinations, so if you're typing two characters and one is with one hand and the other is with the other hand, that is really fast. If you're typing with one hand but the two characters use different fingers, that's also pretty fast. But if you're using a single finger, and in the worst case, a single finger going from a letter to a number, or vice versa, then that takes a lot more time. And so those cases give you a lot more information about what the user just types. It allows you to make a much better guess about what the user typed. Now we get into the guts of the algorithm they used. They used what's called a hidden Markov model. Hopefully I'm pronouncing that properly. Um, an HMM, as it's usually shortened to, is designed, at least the way I think of it, is that it goes backwards. So instead of having inputs and then you do some processing to come out with an output, it actually goes in reverse. What it's designed to do is to take an observation, which is normally, the output, we normally think of as an output, and then take that and then the training data that tells you how you might go from and that what kind of inputs might give you that output, and then allows you to go backwards and get an idea of what inputs tend to make that kind of output. So there's an example in another paper that I think makes it clearer. So let's say you have you want to measure the general temperature from a century or two ago, back before they had temperature readings. What you can do is go look at a tree and look at a really old tree and look at the tree rings, because you get a new tree ring every year. And then using more recent data, you can train a model to say, okay, if a tree ring is this size, then it's likely to be a warm year, and or if it's small, it's tend to be a cold year, or whatever the distribution is. And then you plug that in, you make that your model, and then you take these tree ring sizes, and then you get a guess, a probability of it being a hot year or a cold year. And that's what they do here, because here we have these observations of the latency between two keystrokes, and then of course a series of them as the user types a password, and we want to get the probability that it was a particular pair. And as we'll see, we want actually a lot of, we want all the we want the most likely pairs that give us this observation. And so just to repeat what I said, we have training data and we have these observations, and the hidden Markov model is a great fit for what we need, because we don't know the inputs, we don't know what we know that characters come across, but they're encrypted, and so we need to find a way to get back from these observations we have and this training data we have and figure out what the inputs rather were likely to be, and that's where an HMM is a good fit. Now, to make this model work and to be better than just brute forcing passwords, you need to make it fast, because in the basic sense, a hidden Markov model, when you're dealing with all of the possible keyboard combinations, is going to take exponential time, and that's no better than just brute forcing the passwords, which also I presume be exponential time. But you can use dynamic programming, and we'll get to this in the next slide, to reduce this to polynomial time so that you can make the algorithm work quickly enough to be useful for you. So the magic that makes the hidden Markov model work is something called the Viterbi algorithm, and I'm sorry if I'm mispronouncing that. What it is a way to efficiently go through a state machine, or a series of states, and find the shortest path to get from one state to another. And so to make that work, we're talking about shortest paths, but we want the highest probability. To make that work out, we take the negative natural log of all of our probabilities, which basically inverts them, so that higher probabilities end up being smaller numbers or shorter paths, and it fits with the Viterbi algorithm. Now, what makes it better, what makes this run in polynomial time, is that as it goes through the model, as it goes through all these states, it throws out almost all of the data, because if I've got two ways to go from, or two ways to reach a state, at the end I only care about the shortest one, so I'm going to throw out everything else. So in the basic Viterbi algorithm, at each stage, if you have n states, you only have n paths that you keep, and so that allows it to work in polynomial time. The paper's authors realized that if all you keep is the best path, you're likely to be, there's a good chance you're going to be throwing away the real one unintentionally. Because say, for example, if the real key combination is G and 5, well, F and 4 is going to be very similar. And so, and if it ends up being just slightly higher probability based on the key timing you recorded, then you keep that and you throw away the real one. Whereas, and then you might be keeping like F plus F or F plus G that's going to be faster. So what they did is they modified the algorithm to keep not just one path between, or one path reaching each node, as they keep n, and they just set a number n, keep a certain number of those paths reaching each node and then keeping that along. So you trade off some speed because you're keeping extra paths for not throwing away uh, a result just because it's not quite as good as another one. Whereas with keyboards, there's going to be a lot of variation. In fact, there's a lot of overlap between the latencies depending on what keys you're typing. So you can't simply throw away the not quite as good one when it might be the one you're really after. So the authors took this new algorithm and they applied it to some real passwords, and they created little program called Herbivore that attempts to guess at passwords. So they took a single user first, and they had them train the model with their key timings, and then they had them learn and then type 10 passwords. And they found that for at least half the cases, they were able to guess the password with just 1% or less of the actual possible passwords. So you think, if you're just brute forcing it randomly, you're going to have to try 50% on average. They did it in 1%. And then actually there was just one that was like 14 or 15, 16%, something like that, that made the median, or made the mean, sorry, made the mean a lot longer. It's 2.6 instead of 1, but they were able to get a lot of passwords with not nearly as much effort. Now they extended this to take training data from one person and apply it to a second person, and while the results weren't quite as good, which you would expect going from one person to another, it was still able to improve greatly on just brute forcing the password. So really interesting attack, but in thinking about it, um, I have some ideas for how they might improve the algorithm they came up with, how they could really extend it. And these are just, of course, my opinions. I haven't gone to look for what anybody else has come up with. I wanted to just say what I thought about. One of the improvements is to get more training data. This, of course, was a small study, but if you can get training data, keyboard timings, keyboard latencies between lots of different people, then you can, in theory, build a better model that's better able to handle a wide variety of people. That's one thing. Another way they can improve things is attempt to do some classification before they actually run the model. So, for example, if one person is a touch typist and another person is a hunt and pecker, they're going to have different latencies. In fact, you figure the hunt and pecker is probably going to have maybe more consistent latencies as they're just moving their fingers around, as opposed to moving two fingers around instead of someone with their keys on the home row and moving them around in that way. So if you could do some classification, you could specify a better model to the HMM so that you can get better data out. And the other thing you could do is, and they didn't really talk about this, but you can manipulate the number of passwords you keep, and you can possibly even trim down that number even within the model, and trade absolute accuracy for, if I'm able to get 50% of the passwords by checking 1%, then that's probably good enough to make an attack just to try to get into somebody's network rather than trying to, keeping 2 or 3% of that data and having a much longer runtime on the attacking software and getting more people but taking longer to do it. So I'm sure there's some optimization, there's a trade-off that you can make to make the actual attack faster. And I want to end with a couple of criticisms I had of the paper. And this is, again, my my opinions, things that I came up with while reading through the paper. The first is they talk about entropy more than once and talk about the entropy of the English language. And what this means is that as you type data, you're not actually typing a lot of information. So take a simple example, if you type the letter Q in English, you know the letter U is going to come next. So the letter U being there doesn't give you any extra information. And so they referenced a paper from 1950, I think, 1951, about the entropy of the English language, and saw that it's between 0.6 and 1.3 bits per character, which, taken another way, say you could generally compress written English down probably to that level. That's a good goal to look for. But we're dealing with passwords here, and in fact, they explicitly use randomized passwords. The entropy of a randomized password, the information you get out of a randomized password, is simply the number of possible characters, because this is random. And so typing one character gives you no information about what you type next. I estimated that the entropy that they're dealing with when they had 10 letters and 5 numbers that they restricted themselves to in the study, you could cover that in 3.9 bits. Compress it down to 3.9 bits, or cover 15 characters in 3.9 bits. Now, when you talk about a full keyboard with all the uppercase, lowercase, special characters, numbers, and all of that, if you look at ASCII, you have 94, or 95 if you include space, which gets you to about 6.5 bits of information per character, which means that you've got a lot bigger job than I think the paper is recognizing in guessing at the password as far as the amount of information you get. So I wonder if their results are really going to scale as well as they think. And my second criticism is a little more nitpicky, but they talk about the runtime of their what they call n Viterbi, their modified Viterbi algorithm, as being order of n times q squared t, where n is the number of candidate passwords you're keeping, which is actually a percentage of the overall number of passwords. Q is the number of key pairings, and T is the number of key pairs that you're measuring. It's a little bit misleading to say that it's, the Q squared it bothers me just a little bit, just because you can do better than that. I mean, when we go to the full keyboard, we're actually scaling based on the number of keys we use. And so the number of key combinations would be the square of the number of keys. And so a better representation, I think, of the complexity is order of n times x, where x is the number of keys, or rather number of characters available, to the fourth times t, which is of course still much better than exponential brute forcing approach, but not quite as good as what the paper said. The paper also mentioned a couple of countermeasures. One is rather naive one, they said, is to send just some dummy data as well as the real data to kind of throw off the attacker. Maybe a better one would be to get rid of this latency, varying latency, and then send packets at certain intervals, and also pad those packets so that if I type 2 characters in an interval, it sends 2 characters, and an attacker can't tell the difference. If I sent no characters, it sends a fake packet that's encrypted so that the attacker can't get an idea of any of the timing and would obviate this attack. So to kind of wrap things up, this is an important paper, and as the professor said, this is a huge, cause some shock waves, because SSH is in such wide use for securely logging into a remote server, and anything to minimize that security is really concerning. And despite the quibbles I have with the paper, it's a very concerning attack they came up with. I mean, if you can reduce the time it takes by 50 times, as the paper suggests, or anything close to that, you're going to really reduce the security of SSH, and that's what makes this such an important paper. Thank you very much.